Okay, so for this lecture, what we're going to do, we're going to look at two different topics I want to focus on that are kind of related. One is we're going to look at respiratory exchange ratio, that's called RER. We're going to get into what that is, how we measure it, why is it important. And related to that, we're going to look at how we perform and what we measure during a VO2 max test. And so we'll get into that here in a second. Let me review where we've been. If you remember last class, we talked about the anaerobic threshold, what that is, what it entails, and we spent a lot of time talking about lactate and how lactate is a key part of that. But, and one of the big themes was, well, lactate's not the only issue when it comes to the anaerobic threshold. It's not just that we're building up lactate. Part of it is an inability to remove lactate. We talked about that. Part of it is also differences in isoforms of LDH enzyme and the role that has on lactate. Part of it is NADH and its removal and usage and its role in electron transport. So there's a lot of factors that go into lactate and lactate production and lactate threshold than just simply lactate. And we even finished class saying, hey, and by the way, lactate's not such a bad thing because we can actually use that through gluconeogenesis in the Cori cycle to produce what? ATP. And so it actually may be of some benefit. So that brings us today. We're going to look at RER and respiratory exchange ratio and measuring VO2. But in order to kind of understand that, I want to look at how we measure VO2. Last class we talked about the lactate threshold. It occurs at some percent of what we call VO2 max, which is your maximum aerobic capacity. And so I want to look at kind of how we do that because that'll be pertinent. So that'll be pertinent to looking at RER. So what I want to do, this is a copy of a VO2 max test we've done in the lab. This is a really long test. There's a lot of data on here. I'm just going to focus on a lot of the variables we use. So don't get caught in looking at all the data and all the graphs. There's certain variables I want you to understand. So subject, we did this about a year ago. This is just some of the resting measures. This data right here is some of the max test values. But I really want to look at this graph. And so what we do during a VO2 max test, really what we want to know is how much oxygen, what's the maximum oxygen an individual can uptake. And so if we want to know how much oxygen someone can uptake, we need to know two things. We need to know, one, how much oxygen do they breathe in? And second, how much oxygen do they breathe out? And the difference between those two is what they keep. In other words, oxygen uptake. And not surprising, that changes with exercise intensity. As exercise intensity increases, VO2 increases to a point at which it hits a plateau. And in class, we call that the VO2 max value. And so in this test, what we do, in this subject, we started them off at a pretty low intensity. I think it was maybe 4.5 miles an hour on a treadmill. And every 30 seconds, we do sampling. And what we do, we actually have a mask on their face. We have a tube attached to one end with air they can breathe in, a tube coming out the other end, air they breathe out. We collect that air, we measure it with a metabolic cart, an O2 analyzer, a CO2 analyzer, and we can measure these values. So let me just look at some of these that we look at here. First is absolute VO2, ABS VO2. That's going to be the absolute value of oxygen they're uptaking for that given time. And so each of these is over, I think it's 20 seconds? 20 seconds. We do 20-second intervals here. So when they started, the absolute value, and this is measured in liters per minute. Here it's 0.316 liters. And as you can see, it goes up, not surprisingly, as the intensity of the activity goes up, it goes up. Relative VO2, which is a similar value except we put in kilograms. So this is relative to their body weight. And as you can see, not surprising, this increases 5 mLs per kg per minute to 12 to 16. And it's not necessarily a perfect line. You can see it goes up and down a little bit. Occasionally we have a subject, they breathe a little weird for a few seconds. That happens. But for the most part, this is fairly linear. So we have VO2. We also have VCO2. And this is the volume of CO2 that is produced. And again, we can measure the volume of CO2 brought in. We can measure the volume of CO2 exhaled, and thus we can get VCO2. We likewise measure it in liters per minute, an absolute value. And over here, milliliters per kilogram per minute, which is a relative value, relative to body weight. And not surprisingly, these do go up during activity. That's not very surprising. Now, the value we're going to look at today is RER. And what RER is, we'll see in a little bit, RER is VCO2 over VO2. And so at any given point, if we were to divide VCO2 over VO2, whether it's the relative, whether it's absolute values, that'll give us a number. And that number is almost always between 0.7 and 1. Now I say almost always. It's supposed to be always, but we'll see. Not always. Is it always? We'll get that in a second. So that's RER, and this changes a little bit over time. But you can see these numbers almost are always between 0.7 and 1. METs, all a MET is a metabolic equivalent. And what that is, 1 MET equals 3.5 milliliters of oxygen per kilogram of body weight. So if you want to do the math here, they're at this stage, first stage, they're doing 1.45 METs. If we multiply that by 3.5, you will get 5.108. I'm certain of that. You can pull your calculator out and pause if you want. So that's all METs are. METs give us a means to give a quantifying number to an activity. Here you see percent of fats, percent of carbs that are used. And this is key because this is, we'll see in a second, is related to RER. And one of the things RER lets us know is at any given point, is someone utilizing more fats, fatty acids, or more carbohydrates to form ATP? And so we'll get into more of that in a little bit. Kilocalories, this is a bit of an estimation based on VO2, so I'm not going to get into that. FeO2 and FeCO2, that's the fraction of O2 and fraction of CO2 in the air that's being breathed out. I'm not going to get so much into that because we just use that to calculate VO2 and VCO2, so we'll pass on that. One key thing I'm going to look at is minute ventilation. VE is called minute ventilation. All that is, that's just the amount of air you are breathing in, breathing out over a minute. And so not surprisingly, this has nothing to do with oxygen or CO2. This is just simply volume of air. And not surprisingly, as this activity gets harder, minute ventilation increases. Not a shock there. We think we all can understand. You exercise, it gets harder, you breathe more, not a shocker. Likewise, we see the same with heart rate here. Heart rate, again, increases, not a surprise. I don't think that shocks anybody. Ignore respiration rate. That's not actually accurate there. We have to do some data there to fix that. But those are the basic values we get when we look at VO2. And this is key because now I want to look at RER and this idea that we can tell from a VO2 max test at any given point, is someone using more fats or someone using more carbohydrates at that point. And so we call that respiratory exchange ratio. And what we know is that if that value of VCO2 or VO2 is 0.7, what that means is that at that point, this individual is using 100% fats to utilize ATP. Likewise, if this value is 1, we would say that this is 100% carbohydrates. Now, I'm just going to tell you, it's never 0.7, and it's almost never 1. It's usually a number in the middle. And that makes sense. That depending on the activity, the dynamics of it, the intensity of it, this value will be somewhere between these two. Even when we're sitting, it's not exactly 0.7, and in the most intense activity you do, it's not actually always 1 either. We'll see that a little bit later. And so this RER becomes really important. So you may ask, well, Dr. Mitchell, how do we get to that? Do you just make up this number? I mean, why? Why do fats have a different number of carbohydrates? What's good? What's bad? Why do I care? Well, let's get into the chemistry a little bit. And again, I know this is physiology, this is not biochemistry, but I want us to kind of grasp what's going on here. And so let's go back to nutrition. If you remember from nutrition, carbohydrates, all carbohydrates are C6, H12, O6, glucose. And so if we wanted to oxidize carbohydrates, if we want to utilize a carbohydrate, what that requires is 6O2 right here. And what that does is that produces 6CO2 and 6H2O. Now, if you recall, you can review notes from glycolysis. When we convert from pyruvate into the Krebs cycle acetyl-CoA, we produce CO2. And also a byproduct of one of the steps in the citric acid cycle. So Krebs cycle is also CO2. And so in here, what we can see is that, okay, well, if I want to oxidize carbohydrate, C6H12O6, I need 6 oxygen, and I will produce 6 CO2. Well, 6 divided by 6, you don't need a calculator for that, is 1. And so not surprisingly, if we're just using carbohydrates, the RER is 1. Well, let's look at fats. Well, fats, totally different chemistry. Again, if you remember from nutrition, They're really long fatty acids. They generally they have even number carbon chains on them. And so fats are C6H32O2. Well, if we need to oxidize fats through beta oxidation, different step, we need 23 oxygen, and the byproduct of oxidizing that is 16 CO2 and 16 H2O. Well, with that, we have 16 divided by 23, and what number do we get? Let's move you up. Boom, 7.7. And so if we're just using fats, the RER is going to be 0.7. Okay. So like I said, these are perfect situations that they're really kind of boundaries. It's almost never 0.7 and it's almost never 1. It's usually a number in between, and this is depending on the activity. And so when we look at lower intensity activities that don't require a lot of effort generally, we usually say that fats are the primary fuel for that activity. In more high intensity exercise, usually we use more carbohydrates. Now, there's a lot of reasons for this. Fast twitch muscle fibers, which we'll get to in a couple weeks, generally are more glycolytic, and because of that, they utilize more glucose. They're more anaerobic. We've talked about that. And a good way to picture this is actually this slide right here. So we can see as we increase our percent of VO2 max, as we engage in a harder and harder activity, we see that the percent of carbohydrates we use increases, and the percent of fats we use decreases. Again, not a surprise there. We can see both these values. And so, depending on the activity, for most of us, if we're going for a jog, even playing a game of basketball, we're probably not up here all the time. We're certainly not here. We're somewhere in the middle, using some carbohydrates, using some fats. Right? Now, we do occasionally with long-term prolonged exercise. And when I say prolonged, we're talking an hour, maybe 2 hours. We do see a shift towards fat metabolism, and there's a couple reasons for this. The biggest being carbohydrate is a finite resource. Now, we've talked about this before as far as glycogen storage, glucose. We don't have that as abundant as we do fats. And so as time goes on, we generally utilize more fats slightly, and so we will see the RER drift slowly lower typically. Epinephrine also has another role in this. And so that's a key thing to understand, is that with some of this long-term activity, we do move to fats. Glycogen is depleted, reduced rate of glycolysis. Now, having said that, this is long-term activity. I mean, we're talking an hour, 2 hours, which usually we don't always engage in. Usually for most of us, it's 30 minutes, 40 minutes, tops. But we will see that over the long term. Now, one of the things we can grasp from this, and let's kind of look at this graph right here, this kind of sums it up, is that, hey, as we increase, as we go to longer duration activity, right, which obviously requires a little less intensity. We can't operate it at 100% intensity for 2 hours. It's not possible. So if we're going to increase duration, we have to decrease intensity. Well, as we do that, not surprisingly, we're using more and more free fatty acids, FFA. The amount of that utilizing to form ATP becomes much greater. Here we can see muscle glycogen depletes, and truth be told, this line probably should come down that way. Blood glucose, assuming we are restoring that, because you would need to at some point, 2 hours in, that's also decreasing. So we're seeing this shift from carbohydrates to a little bit more fatty acids again, because we have more of them, we have more storage of them, and as we've talked about way back in bioenergetics, they form more ATP. So it's a really good deal. Aerobically, but they form more ATP. Okay, so this is going to finish up our chapter 4 here in exercise metabolism. Our next chapter we're going to go forward in is acid-base balance. We're going to get deep into that and hydrogen ions, why they're important, not just in activity, but clinically, and what the big deal is there. I encourage you to look through your book in this chapter. I said in lecture, this is one of the harder chapters, so follow along in your book. Review some bioenergetics to make this make a little more sense. And we'll see you at the next lecture.